Hi everyone, today we're going to talk about sections 4.4, 5.2, Fundamental Theorem of Calculus. I'll say right away that this lecture is also going to cover the stuff that's in 5.1. This is more to do with like some graphs that we're going to see in a minute. I think it makes a little more sense to talk about this part first, but we'll get there. So, Fundamental Theorem of Calculus, that sounds important, right? If we think about what we were doing last time, we were doing graphs of functions, we were looking at the area under the curve, and we were thinking about a way to come up with that area by adding up a bunch of rectangles. We had this sort of big definition where we said a definite integral from a to b was this thing that we got by adding up all these rectangles and then sort of taking a limit, doing more and more and more rectangles, and that was approximating the area under the curve of my function. So that was kind of a lot of work, and I promised you last time that there's going to be a better way to do it in the future. So that's basically what we're talking about today. This course exists because of this better way to do it, basically. So it's good going forward. It's going to be important to keep in mind the Riemann sum idea that all we're really doing is sort of adding up rectangles and maybe making more and more rectangles. But we're going to learn lots and lots of techniques and shortcuts for kind of getting that area number without doing all this work. Like, you might remember we did this where I had all these like sum identities and everything, and it took forever. So we're going to build to avoid all that. So the starting point is this thing that I'm going to call an accumulation function. So say we have a function, f, and it's over some interval ab. It's continuous, so I can draw the function without lifting up my pen. Maybe here's a and here's b. So it turns out that this accumulation function that I'm about to describe is kind of the key idea here. So this is a little bit confusing, so you have to be a little bit careful. Let's just think about this integral on the right hand side first. So if I have a little f function already, I can pick an x value to integrate it from a, my left hand point. So let's say I pick an x that's right here. So I could figure out the area under the curve from a up to that point x and get the area under the curve up to there. And so I could write that as the integral from a to x of my little function f little f. So that's fine, that's going to be some area number. But I could also imagine picking some other x value. So say I didn't like this x value and I wanted this x value instead. Then I could maybe call this x1 and this x2. So my original integral was x integrating from a to x1, but I could also integrate from a up to x2, and that would be a bigger area, right? It would be going from a all the way up here to x2 and getting all that area. And yes, I would write like this. I could imagine picking even more x values. Maybe here's x3, and that would be the integral from a up to x3 of my function dt, and that would be integrating again from a all the way up here to x3. So I can integrate more and more to the right, all coming from a. I can go from a to some point, a to another point, a to another point. I can get more and more area. Kind of the more to the right I'm going, I'm accumulating more and more area under the function. So that idea is going to be called an accumulation function. The thing that's a little bit tricky to think about is, so given little f, I want to define a new function whose name is capital A, and that function's job is going to be do the integral up to x, right? The function has an input, right? It has this input x. What am I going to do with that x? I'm going to use that as my right-hand endpoint for where I'm going to integrate to. So I could say a of 1. What does that mean? A of 1 is my input, it's x, so that 1 is going to go where the x would go. So it's a little bit weird. I'm using this 1 as like a parameter, like instructions, for what integral I'm going to do on the right hand side. Remember, this integral is just going to give me some number, which is going to be the area. So a of 1 is some number, and I find that number by integrating from little a up to 1. But I could do my accumulation function at some other point. Accumulation function of 3. So 3 is the input to my function. I put that 3 where the x would go, so up there. And what this means is again, this is going to be some number. A of 3 means take the number 3, that's the location I'm going to integrate my other function up to. So a's input is the instructions for how far to integrate this other function, f. So just make sure that makes sense. That can be a little trickier. I'm defining a new function of x. Where does that x go? It goes here in the upper endpoint of my integral. So the input to a tells me how far I'm going to integrate this other function, f. So it's a little tricky, so just make sure that that makes sense. This a is not like there's only one a in the world. If I had a different little f that I started with, then I could build a different a, right? Yeah, I could have multiple graphs. I could have one function which does this, I would call that f, and then I have some other function which does this, call that g. I could make an accumulation function for f, and I could make an accumulation function for g. So a of x for over here would be integrate f from the beginning up to x. And the accumulation function on the right hand side would be integrate g from some point up to x. So I integrate g instead. So the inside is this g function. I guess I should just have of t here. So that doesn't look very good. So really, if I was being careful with my notation, maybe I'd want to call this like AF and AG, like the A function that has to do with G and the A function that has to do with F, something like that. But from context, if that's clear, we just write A of X, usually. Okay, so just quick visual, right? If here's my function F, then, right, here's A, the beginning. If I do big A of that start point, I'm just integrating from here up to here, which is going to be 0. We know that was one of our rules. If I integrate, right, from one number to the same number, whatever my function is, I get 0. That was one of our integral rules. And then I could go, like A of 1, maybe here's 1, that would get this area. Then I could do like A of 2, here's 2, it would get up to that area, the whole thing from A to 2. Etc. So why do we care about this? Well, it turns out that the way to think about what is an easier way to compute this area instead of doing Riemann sum ends up being a connection between doing integrals and doing derivatives. It turns out that this A function is going to be interesting if we take its derivative. It's going to tell us something about the original function. So let's think about this for a second. A of x. So I'm given some function g in the background. So or some function f in the background, and has a starting point a, ending point b. Now I'm going to build this new function a of x. I'm going to call this f of t. What does a of x say? It says integrate f from little a up to some point x. So remember, this a is a new function, right? I started with f and I built a new function. My new function is integrate f up to some point, and that some point is the input to my function. Let's try and think about what it would mean to take the derivative of this new a function. And I have to be careful right away. Like this is not like the derivative of f, right? I made a new function, capital A, and I'm taking the derivative of that new function. Right? You might remember another way to write this would be like dA dx, and maybe another way to write this would be ddx of whatever a is, which is this function, this expression that we wrote earlier. So we might see all three of these ways to describe the same idea. We're taking just three different notations. We're taking the derivative of this capital A. Okay, what could it possibly mean to take the derivative of this? Well, let's just think visually in terms of this picture. Say, let's maybe draw this a bit bigger. A, B. Say I had x right here. Right, so just remember, what does the derivative mean, right? Like if I do the derivative of a function, it's kind of like taking the slopes of the function, right? Like if I do something like this, if I want to take the derivative at this point here, I imagine, okay, let's pick some point that's kind of to the right here, maybe x plus a little bit. Look at the y value there. Now I can make a slope, a secant line they call it, a line that connects those 2 points. That sort of has a slope, and that slope is like this rise over run right here, right? What I can do then is pick another x value, which is even closer, maybe x plus 1/2 or something. Look at that y value, draw a slope there, right? And that's a new line with a new slope, and we imagine making that smaller and smaller, getting x values closer and closer to this original point. That picture is maybe not the best picture. If it's something like there's my first slope, and then there's my second slope, and there's my third slope. As you get closer and closer, it's sort of approaching what we might think of as the tangent line to your curve at this point x that we started with. So it's nice to think about that visually on the graph, but we can also think about it just sort of procedurally, right? What am I doing? I'm taking a step to the right. That's kind of getting this delta x, this change in your x position. And when I do that, I'm getting a step up. And I'm going to be dividing those two numbers to be thinking about sort of what my slope is. So really, a way to think about this derivative is like, you could say like in quotes, like when x increases a bit, a small bit, how much does my output increase, right? If I take a little step to the right and I get a big increase in output, that's a big slope, that's a big derivative. If I take a little step to the right and I get a small increase in output, then that's a shallower thing with less slope. So that we can think of that logic for this a prime, right? I'm taking the derivative of a. So if I want to take a little step to the right and see how my output changes. So say we're starting here at this x. First of all, what's my output right now? Well, I'm doing a of x, right? Remember this graph? This graph was little f, my original background function. Big A says integrate little f from a up to this point x that I chose. So if I integrate from a up to this point x, my output right now is the area under that curve. Okay, so that's my current output. Now I'm going to increase x a little bit to the right. So we imagine bumping it up here. Maybe call that x plus 1. Now I want to see what the new output is there. So if I do a of x plus 1, what does that mean? I'm integrating my original function from a up to this new x plus 1. So before I was integrating from a up to x, but now I'm integrating from a up to x plus 1. So I bumped my input up, and we can see how my output changed, right? Originally I had some area whatever this original area was here. But then, now I have a new area, the big red area. So, the sort of difference between those two areas is how much change I got, how much more area I get when I increase x a little bit. Right, how much more area do I get when I increase x a little bit? So we can see, like, the difference between those two areas is sort of this part, right? So, like, whatever the area of that piece is, that's sort of how much new area I get when I increase x a little bit. Which means I can think of that green area as the sort of like the slope of this line. It's like the value of the derivative, right? The derivative is how much more output do I get when I increase x a bit. So here, this area is how much more output I get. So, like, this green part, like, sort of is a prime, kind of. Now, it's only in quotes a little bit because the actual plan is to do like what we do over here, and not just pick x plus 1, but maybe also pick x plus 1/2, right? And then pick x plus even smaller. So you can see what's happening, right? If I pick smaller and smaller values, my green sliver is going to get smaller and smaller. In fact, if we, let me just draw this here maybe, if we imagine sort of going all the way to x, what do we think the green sliver would look like? Right, at the beginning it's kind of fat, but it would get skinnier, and as I make my x plus 1 thing like closer and closer to x, I would end up just getting maybe this right here, right? Oh, that should be green. Why is it not green? My green sliver would end up being just like a single sort of vertical line right at x. Maybe something like this. So, okay, so what we have now is we believe perhaps that to talk about the derivative of this a function means the limit of this process means whatever area this sort of green sliver is. So what does this area, this height maybe, have to do with our original function? Well, like the height of this rectangle, this like kind of, you know, quote unquote infinitely thin rectangle, the height of it, like, it's totally just f of x, right? Remember, this function was little f, so the height of this kind of green sliver is totally connected to just what the actual height of the function is at x. But back in this picture, right, the height of my function f, like here, like that's the height of f, and then because of the shape, like there's sort of various heights of f all along this range here, and the area of this green rectangle clearly has something to do with the height of f. It's maybe something like the average height of f over this interval. But as it gets smaller and smaller, that sort of just becomes actually the height of f, or the f of x value. So all of that is to say that when I take the derivative of this big capital A, what I'm actually going to get out of it is in fact exactly f of little x. So the point really of this accumulation function is it's a function whose derivative ends up being my little f that I started with. So that's kind of a big deal. Remember at the beginning, like in the first day, we were talking about finding antiderivatives, like coming up with a function who is the derivative of my given function, right? You hand me a little f, and then I try to come up with a function whose derivative is little f. We did some examples, like if this was x, then I could come up with like x squared over 2. Just check that when you take that derivative, you get my little f back. We had to like actually think about this process like algebraically. It turns out now, right, if I give you this x function, I can actually come up with an antiderivative, like sort of without even doing this. If my f of x is just x, then and you say I want an antiderivative for this, I'll say, okay, here you go. Capital A with that guy. Integrate from a to x, yeah, so, right, f of t dt, but in this case we know what f is, so I'm going to put a t here. Right, if I imagine plugging t into this, t is going to pop out, right? Because, like, plugging t in means put a t wherever there's an x. Like, if this was x squared, then I'd end up with a t squared inside here. Okay, so the point is, if you hand me this function, f of x equals x, and you say you want an antiderivative, I'm like, yeah, here you go. This is an antiderivative. A of x is that integral. It's a function whose derivative ends up being f. We can check. I mean, I argued it, but according to my argument on the right-hand side, the derivative of this capital A is in fact x, which is the original function f. Now, I didn't really do any work there to find that. I'm citing like this result, this claim that the derivative really is the original function. So maybe just for clarity, I should write a prime of x is apparently f of x, if you believe my story on the right, which is just x. So you hand me a function, I say here's an antiderivative. I don't have to do any algebra or think about these rules or anything. It turns out basically what's going to happen is that, well, okay. So that's already kind of cool. We can find an antiderivative. The real reason I care about that is that I want a way to evaluate integrals, right? I want a way to find areas under curves. That's the whole plan. So what this relationship is telling us is that, oh, there's going to be a connection between getting the integral and this like algebra process, right? If I know that on one hand the antiderivative of this guy x is supposed to be x squared over 2, but on the other hand I know that the antiderivative is supposed to be this guy, this integral, then that gives me a connection between this sort of process of turning x into x squared over 2 and evaluating this integral. I'm going to be able to find the area under a curve by doing one of these like algebra antiderivative things. So that's the upshot. So we'll see how that works in detail in just a second. That's the idea. So you don't have to worry about knowing this entire story super clearly. This is really just like a sketch of like why it might be true, just to give you a feeling like you could maybe have discovered it yourself. But our plan is basically going to be using this a of x thing and using this result, the fact that its derivative is actually this f that you started with. So I'm going to scroll back over, summarize some of this stuff, and look at some examples. Okay, so this is fundamental theorem of calculus, part 1. So if we just have some function, I can define this accumulation function, which we've talked about a bunch. I integrate from a to x, my input, and I integrate my original function. So it turns out that this function, in fact, does have a derivative, and its derivative is my original function. That's what this says. So given little f, write down this guy. That guy will be an antiderivative of little f. And usually we're going to kind of summarize it like this. If you see this in a box, that's probably what someone would just call the fundamental theorem of calculus. The derivative with respect to x of the integral from a to x, f of t dt, is f of x. Notice, by the way, that it kind of looks like I don't know, like if I have f here and I have f here, it kind of looks like the d dx and the integral sign are sort of canceling out, leaving just the little f on the right. That's kind of a way you can think about it. The derivative is sort of undoing the integral. There's a little, it's not, you have to be a little careful because there's the variables, right? Inside here, it's f of t, and there's an x here, and then there ends up being an x right there. So just symbolically, that's what's happening. The x, right? The x is really the place that I'm integrating up to, right? big A says integrate my little function f from a up to x. So that's like what the x is meaning. And the height right there is f of x. And that's going to be the value of the derivative of a, big A. What the t is doing here is kind of just being a placeholder, right? If I'm going to integrate little f from a up to x, I need to integrate, like it's a function. I need to have a variable that I'm integrating with respect to. Like as t goes from a to x, t is tracking like what the height of the function is between a and x in order to do the Riemann sum thing. You could write f of x dx inside instead. It would just be sort of confusing because x already is being used to name this place where you're integrating up to. Okay, and as we said, this means a is an antiderivative. So it's a function whose derivative is this f that we started with. Okay, so that's just kind of unpacking what all that means. Let's just look at some examples. This is a problem you might see. It says, hey, compute this. What's d dx of integral from 1 to x, cosine t dt? So cosine is like our f of t. D dx, right, so our theorem says that to take the derivative of the integral, by the theorem, I just need to just grab our original function. So the answer is going to be f of x. I identified f was cosine of t, so this is just cosine of x. That's it. D dx of 1 to x cosine t is just cosine x. There's like no work to do. I don't have to do any algebra or anything. I'm just literally copying what's inside, but writing an x instead. I could do 100 more examples like this. I could go from 1 to x of sine t dt, and the answer is sine x. So there's no work to do. You could imagine doing a Riemann sum or something to like figure out what this would be, getting some function of x, right? And then taking the derivative of that function with respect to x. That would be a crazy amount of work. If you did that, you would in fact end up with the sine of x on the right. But this is like a big shortcut to that process. So if you see a problem that has like the d dx right next to the integral, don't think that that's asking you to like do an integral and then do a derivative. It's prompting you to think about fundamental theorem calculus and use that shortcut, where they basically cancel each other out. Okay, there's a couple points here with this example that we actually didn't really mention earlier that are important. This whole time I've had like some a starting value on the bottom. I've just been drawing a right here. Here we have a specific starting value, which is 1. I didn't really talk about the a that much. It turns out it doesn't matter, right? If we think back at our picture, right, what's happening with this green slice, it only depends on like what's happening with the function around this zone, right? It's not really paying attention to what's happening on the left over here. And in particular, if our function actually was starting like here instead, like a plus 1 instead, as long as that's not like in the right hand zone, it doesn't matter. The behavior only depends on what's happening around this point x. So what that means is that, in fact, if I put like 1 to x, and I do this whole thing, f of t dt, that's f of x. But also, if I do that same whole thing, but put like a 100 down here, put some other number down there, that's also just f of x. So the theorem, sorry, it's a little sloppy. This is a t, this is a t, those are x's. The theorem does not care what number is down here. It could be any number, and the theorem still works. You just get f of x on the right side. So in the theorem statement, that's kind of taken care of by just having an a here, but it could be anything. So in this problem it's 1, but if it was a 2, it'd be the same thing. Okay, let's take a look at this next example. So here we have d dx of the integral from x to 0 of this guy, which is written currently as dp over p squared plus 1. So first I just want to mention, if we haven't thought about this yet, when I write this, it's the same thing as writing 1 over p squared plus 1, and then dp on the right. So this is a little more familiar, and I like this better. It's like I said before, this integrals like brackets. Like there's the left hand bracket, the right hand bracket, and then here's my function inside. It's common for people to write it this way. What they're imagining is kind of moving this dp into the top of the fraction, sort of like you're multiplying it through. Now this dp is not like a number that we actually can do like fraction math with, but it's a sort of historical notational convention that you might see sometimes. So I wanted to have an example with it. You can kind of think of it as being able to multiply in like that, but not really. So ask me if you're curious about that. So the point is we should just translate this into d dx of x to 0, and then it's 1 over p squared plus 1 dp. Second thing to mention here with the variables is, yeah, there's a p inside. dp, p squared plus 1, that's fine. It could be a t. I don't want it to be an x because I'm kind of already using x, but it could be any letter and you're still doing the integral. Okay, so we want to apply our theorem, right? We don't want to like do any hard work, we want to take the shortcut. Only problem is, according to the theorem, x has to be in the top. That's like how it's stated. Probably, you would guess that a similar version of the theorem works if there was an x in the bottom instead. It doesn't seem that different, especially if we think about our picture over here. Right? If we were going like from a point x up to 2 or something, then my a function would just be like talking about maybe the place I'm starting to integrate from, kind of thing. So we could imagine kind of going through all that same logic, but that's actually kind of more work than we need to do. If we just remember, one of our integral rules was that we could flip the sign of the integral. Flip the order of the bounds of the integral at the cost of putting a minus sign in front. That was one of our integral rules. So what that means is that here, I can say, well, I don't have to think that hard. I can just say this is the same as negative integral from 0 to x of the same thing. And this negative sign maybe I'm not happy with, but we can pull it out, right? One of our derivative rules is if I'm doing the derivative of a number times something, that's the same as pulling that number out in front of the derivative. And now I'm happy. Now I'm all set up to use fundamental theorem of calculus. I have something which looks exactly like what's in this box. The x is in the right spot, and I can just apply it directly. So don't forget the negative sign. Then this right hand thing just becomes f, meaning this inside function, but with an x plugged in. So 1 over x squared plus 1. So by rearranging the thing that we were trying to take the derivative of a little bit, we could write it in precisely the fundamental theorem of calculus form with the x on top, and then we could just use it. So we don't have to like have a second version of the theorem with the x on the bottom. We just use the one version with x on the top, and remember that we can flip the integral if we need to, at the cost of a minus sign. So again, not really any work, but you will see problems like this where they ask you to okay, we're back. You will see problems like this where they ask you to like take the derivative of some integral, and it's like in the wrong order. So they're prompting you to think, oh, this is the thing where I can swap the order of the integral, and use fundamental theorem of calculus. in the same vein, let's take a look at this one, number 3. So number 3 here, again, it's derivative of integral, so it kind of looks like I want to use fundamental theorem calculus, but it's not exactly in this format, right? I don't have an x up here. I have this e to the 2x thing instead. It's a little bit weird, right? Well, let's try to think about this in terms of this a function, right? Big A of x. What is that? It's the integral from a to x of my function. And for this function, I can actually write that in here. Log of t squared dt. So that's the big A, capital A, in this situation. So this is not exactly what we have here, right? This is not exactly a of x. It looks a lot like a of x. Is there a way I could express it using a of x? Well, remember I have a function, a, that I can plug stuff into, right? I could do a of 1, a of 2, a of 10, a of x. How about if I did a of e to the 2x? I'm just choosing to plug in this expression, e to the 2x, into a. That would mean, well, whatever my input is, that goes where the x goes, right? So I put an e to the 2x, that's my input, up here where the x would be. And then everything else stays the same because there's no x's involved anywhere else. So what that means is we can recognize this d dx of integral e to the 2x thing as actually d dx of this, right? Of a with something plugged in. So I'm going to kind of write that like this. Our problem statement looks like I'm taking a of e to the 2x and then actually taking the derivative of that whole thing. That's what it looks like. Now, we can remember from Calc 1, I have a function, sort of an expression with a variable in it, that's like inside another function, and I'm trying to take the derivative of the whole thing. So that means I have to use chain rule. I have a function that's inside another function. How does that work? Well, we take the derivative of the sort of outside function, right? This is one way to write down the chain rule. I plug in the inside function to the derivative of the outside function, but then I have to remember to multiply by the derivative of the inside function. Right, that's one way to say the chain rule. Okay, cool. But what does this look like? Well, a prime. Oh, I know what a prime is, right? A is this guy, and a prime, by fundamental theorem calculus, is just this f inside function. So the derivative, right, this function, a prime, is just log of x squared. That's just normal fundamental theorem calculus, because I have just x, regular x, on the top here. The derivative is just the inside function with x plugged in, the integrand with x plugged in. So here, it's going to be log of my input squared, right? So, right, like a prime, I should write like a prime of x is log of x squared. So a prime of something else, like e to the 2x, is log of that something else, e to the 2x, equals. So I'm going to put here log of e to the 2x squared. Right, the e to the 2x is taking the role of the x when I say a prime of x is log of x squared. Okay, and then we still just have the derivative out here of e to the 2x. It's technically another mini chain rule, but just remember that like the derivative of e to the x is e to the x, and if it's e to the something, it's going to stay the e to the something times the derivative of the inside. So I keep e to the 2x, and I times the derivative of the inside, which is 2. Cool. Okay, so what is all this happening? I wanted to do the derivative of something that looks like fundamental theorem calculus, but there's something up there. So that means a chain rule was involved. Look what happened, right? If I just did a prime with no chain rule, just like regular a prime using this guy, I got log of x squared. So that's what's happening here. I'm getting log of the input squared, where my input happens to be this thing. Right, so before I had log of this x. Now I'm just getting log of this input. So like whatever is sitting here up on the top, that's kind of going into your f. Right, if I call f of t log of t squared, that's my integrand function inside there, I could write this here as f of e to the 2x. Right, I'm taking e to the 2x and plugging it into that inside function. And I just had to multiply by the derivative of this guy. Right, which is the derivative of this. So one way you could think about this is you could imagine writing down like a sort of another version of the fundamental theorem, which maybe looks something like this. If I want to do like ddx of, calling it g of x, some function up there, the answer is going to be the inside function, right? But normally I plug in this upper bound x. I'm still going to plug in that upper bound g of x. But then because of the chain rule, like we saw in our example, I'm going to have to end up multiplying by the derivative of whatever that inside function was. So maybe just another example really quick. If I do like, you know, to the square root of x, and in here I have like, I need t cubed in here. So what that's going to be is I just do sort of my inside function, just t cubed. So sort of something cubed, t cubed. But I plug in this. Normally I would plug in, like if that was an x, I'd plug in an x right there. But because it's a root x, I plug in root x right there. But then I have to remember this part. I got to multiply by g prime. So I have to multiply by whatever the derivative, I guess I'll just write that here, the derivative of square root of x is. Which, by the way, right, square root of x is the same as x to the 1/2, and then we can do power rule. You just have to remember that 1/2 minus 1 is negative 1/2. Okay, so that's kind of what's going on in this example. Sometimes there's a chain rule that's happening when you do fundamental theorem. By the way, that's kind of technically always happening, right? If my g of x function happens to just be x, maybe x t squared dt. If I do the chain rule version, it says, okay, take t squared, so something squared, plug the upper bound in, that's x, and then multiply by the derivative of whatever that x is. Oh, but the derivative of x is just 1, so I don't have to times by 1, so I can just write x squared. And now that looks like just like the first version we had, that when I do ddx of 8x, I just copy the inside function but write an x there instead. So that's really one theorem, but the chain rule thing is a little bit tricky. Okay, so we talked a lot about this accumulation function. I promised earlier, when I was kind of waving my hands, that we're gonna get some connection between antiderivatives and this accumulation function. Let's just spell that out. We can think about this, right? Okay, so we want to see what this theorem, this fundamental theorem, has to do with this integral. Remember, we're interested in that integral, right? It's have my function f, I go from a to b, I want the area under that function. That's the whole thing we've been interested in. So far, we only have Riemann sums, which can do that. We can do something better using our fundamental theorem. The only thing is, currently, our fundamental theorem says that, like, if a of x is this integral, going from a to x of my function, then we know that the derivative of this guy is in fact my original function, but with x plugged in. So that's our current fundamental theorem. So, right, I have integral from a to x, so probably that has something to do with integral from a to b, if I could just maybe rearrange this in the right way. So, it turns out to make this argument, there's one more crucial piece of information. So you might remember this from Calc 1, but I'll just remind you that if I have two functions, say like capital F and capital G, if I have two functions whose derivatives happen to be equal to each other and equal to some third function, maybe called little f, then in fact this big F has to be almost the same thing as the big G up to a constant. So maybe I'll write f of x here. Then the function big F of x has to actually match the function big F of big G, but maybe plus a constant. So like an example of that would be like if I know that like x squared, I know its derivative is 2x. Also have x squared plus 1, its derivative is also 2x. Those are two functions whose derivative is the same function, and we see that these two functions are different from each other just by a plus 1, by plus a constant. So we already know that. This claim is going kind of the other way, saying that if the derivatives match, then actually the only way they can be different is the constant being different. Like there's not like some weird like crazy function that I can come up with or whatever that also happens to have 2x as its derivative. The only functions with that derivative are x squared and then plus a constant maybe. So we've used that before, so just kind of remember that. Okay, so we have a of x. I want to get b into the picture, right? I currently am interested in this integral from a to b. I have an integral ax, which involves integral from a to x. So maybe something worth trying to think about writing down is a of b. So if I do a of b, that's integrating from a up to b of f of t. So that's one way to express this integral that I'm interested in. Right, the integral from a to b, one way to say that is big A of b, because I have this accumulation function. Okay, so let's just kind of keep that in mind for a minute. We also know that a prime of x is my little f of x. That's my fundamental theorem. So let's imagine that I had some other derivative, some other antiderivative of f, some other big, suppose we already knew about some big f of x, who is the antiderivative of little f. So I know already, given my little f, I know that a is an antiderivative. Let's just imagine I had any other antiderivative, big F, just for the sake of argument. It's big F is some function, big F prime is little f. Its derivative is little f. We know by this thing that I cited a minute ago that actually if I have some other antiderivative that's not just a of x, it's got to be pretty close to a of x, right? A of x is not the only antiderivative, but it's pretty close to it, right? We know that if I have any other antiderivative, it can only be different by a constant. So this means is that a of x, a and f are both antiderivatives of little f, so that means that a has to be big F plus a constant. So that's just using the statement above. If I have two functions whose derivative is the same function, then those two functions have to be equal up to a constant. So one is equal to the other plus a constant. And that's really just kind of an abstract way of writing what we were talking about over here. two functions, same derivative, they have to be the same function, except maybe plus a constant. So bear with me for just a minute, that's kind of the weird abstract part. Now we're going to see how this all comes together. So we know that on one hand, a of x better be big F of x plus c, and in fact, I bet we can figure out what this c has to be. It's not just plus any old constant. I can actually do some algebra to figure out what that c is, right? C better be, I can subtract both sides, right? So I can do a of x minus f of x. But what's nice about having equality between functions like this, right, this constant c is equal to this right-hand side, where there's an x on the right-hand side. That means it has to be true for any x. So this is an algebra trick that we'll use now and again. If I have an equation with functions in it, it has to be true for any x, which means I'm allowed to plug in any x that I want to and see what happens. So let's see what would happen if I happen to plug in little a in particular, right? Why is that a good idea? Well, this is the integral from a to the input, a to a of f of t dt. And this is something, I don't know what it is. But this is kind of being clever, right? Big A is this function. If I plug in little a to it, the same as the lower bound, I get an integral from one point to the same point, which we know is actually equal to 0. That's one of our integral rules. So, again, if I have this other function, big F, whose derivative is little f, I know it's related to a. A is in fact big F plus plus some constant, and you actually know what the constant is. Based on this equation, the constant better be 0 minus f of a, so negative f of a. So if I hand you this big F, which is some other antiderivative of little f, then a is actually related to it, and specifically, a of x has to be that big F of x that you gave me minus f of a. So it's very specifically, you give me an antiderivative big F, I could tell you how it's related to big A by plugging little a into this big F. I get some number. Okay, we are so close, right? This is pretty cool. A of x, right? That's an integral on the left-hand side. F of x, f of a on the right-hand side. That's just some algebra stuff that I might, right? These are supposed to be antiderivatives, right? Of little f. So if I have some process for finding antiderivatives that I've been able to write like an integral on the left-hand side in terms of these antiderivatives on the right-hand side. And in fact, just to kind of go the very last step here, a of x is this particular thing where x is plugged in. But I'm interested in this integral, right, where there's a b plugged in. So, right, a of b, that would be plugging b into this upper part, and that would be this integral. So a of b is this integral, a to b of my function. That's this integral I'm interested in. But by this equation right here, that's actually, right, f of x minus f of a. But what's x? X is the thing I plugged into a, so it's b. So this actually is my big theorem. This is really awesome. This says, remember, what was big F? It was some antiderivative. So this says that if I want to evaluate this integral on the left-hand side, instead of doing a Riemann sum, all I have to do is come up with big F, which is, find some big F whose derivative is little f. Find some antiderivative and plug in a and b. That's all I have to do. So that's really cool. Let's see an example right away. This is kind of a nice statement. So it says use fundamental theorem to evaluate each integral below. Okay, so my little f here f of x, I guess, is 3x squared. So our theorem says I just have to find a big F that has its derivative is little f, is 3x squared. So that's an antiderivative. That's what we were doing on the first day. Can I come up with a function whose derivative is 3x squared? If I can, then to evaluate this integral, I don't have to do any Riemann sums. I can just plug in 0 and 2, the top and bottom number, into that function that I find. So we just have to think about it, right? We started maybe learning some rules, right? In order to end up with an x squared, I probably had to have started with x cubed, right? This guy's derivative is 3x squared. Oh, that's it, right? If there was a different number in front, then maybe you'd have to think a bit more. But in this case, x cubed works. So I can take big F to be x cubed. That's a function whose derivative is 3x squared, which is my original function, f of x. So I found some antiderivative. It was really easy. I didn't have to do like a lot of math. I mean, I had to think about doing the derivative backwards, but as long as I can do that, like that's not a Riemann sum. I have to like add a bunch of stuff and take a limit. I just have to kind of think about what the antiderivative would be. Now we can evaluate this integral by just doing big F of 2, that's the top number, minus big F of 0, that's the bottom number. These are both big F's. And I can do that. What's big F of 2? Well, big F is x cubed, so it's 2 cubed. And then big F of 0, it's 0 cubed. So that's 8 minus 0. So boom, I just did this integral in like, a couple seconds, assuming that you can find this thing. And this really is the area under the curve. Like if I graph 3x squared, it looks something like this. I go from 0 to 2. It's like a weird area, right? It's not like an obvious, like, how much area that would be. I could do a Riemann sum to find it, but in fact, this integral will find it, and it's 8. So that's pretty cool. Let's see another example right away. So I want to integrate from 0 to 2 pi, the function 2 cosine x. So again, little f is my 2 cosine x. So I just need to find a big F. I need to find an antiderivative. Well, what do I know about cosine? I know that sine and cosine are related by derivatives, right? I have to remember the rule, but the derivative of sine is cosine, right? So I bet if I pick 2 sine of x, that'll work. This function's derivative is 2 cosine x, because the 2 doesn't matter, right? And then you just take the derivative of sine to get cosine. Okay, so that's my big F. So I just have to plug 2 pi into my big F, and plug 0 into my big F, and subtract them. So f of 2 pi is 2 times sine of 2 pi, and minus 2 times sine of 0. So there's a little bit of evaluation. I have to remember my trig and or use a unit circle, but I can get a number here. Sine of 2 pi is 0, and sine of 0 is also 0. So I actually get 0 out of this whole thing. So that's cool, right? I could graph 2 cosine x. It looks something like this. And if I'm going from 0 to 2 pi, what this is telling me is that area is actually 0, which means I am doing something like this, right? The top area is totally canceling out the bottom area. Actually, this is not quite right? Because remember, cosine starts at 1, it goes up to 0, and by the time we get to pi, it's negative 1. So this is pi here, right here. And so to get all the way to 2 pi, I'm back at 1 again. So 2 pi is right here. So in fact, I'm going up to there. So that total area is 1. So this kind of like half circle, semicircle thing, they're not circles, but this shape is sort of twice one of these shapes on the side. They add to 0. Okay, cool. So this is our fundamental theorem. We're going to be doing the whole course using this theorem. The only hard part of this is this part, right? Coming up with the antiderivative. So in fact, a lot of what we're going to be doing is figuring out how to come up, like all different methods for coming up with antiderivatives. It's not always easy. Cool. So these say you try, so I encourage you to try these. I'm going to give you maybe a hint first, which is I'm kind of like doing a lot of writing up here just to be clear for the first couple times. But once you kind of come up with an antiderivative, you can just kind of like write it down, right? Like if I remember power rule, the antiderivative of x squared is going to be x cubed over 3. So I'm going to have 9 x cubed over 3. I can do the antiderivative of each part separately. So this will be x squared. That's something, but when I take its derivative is 2x. And then this expression is the thing that I'm going to be plugging in 2 into and 0 into. A really common notation for this is to write this down, and then write like this kind of bar on the right hand side, and put the 0 and the 2. And that's just like reminding you that I'm about to plug in 2 and 0. Like the plan is to plug 2 and 0 into this. So I would write, this integral equals this thing with the 2 and the 0, and then equals, I could start canceling, actually, this is 3. So I'm going to say 3 times 2 cubed. So I'm plugging in the 2. And then I'm plugging in the 2 to this. And it's a good idea to write parentheses, minus, and then like the next set, where I plugged in 0 to everything. It's going to be 3 times 0 cubed plus 0 squared. Cool. And after if you've done a bunch of these, it's totally fine to write like 3 times 8 plus 4 as you go, instead of writing this. And then this is going to be 0, 0. But it's good when you're first learning it to write it out super carefully. I think it's good to write this all out and then simplify. So this will be 3 times 8 plus 4, and then these are all zeros, so minus 0, so just that. So that's 24 plus 4. So that's kind of a template for how you can write these problems. Just kind of start, like first write the antiderivative, write the two numbers plugged in, and then kind of proceed like that. Okay, so give those a shot, and then we'll check out the next section. Okay, so for the last section, so this is kind of getting to the 5.1 kind of stuff. I probably should label this 5.1, sorry. So we have now this accumulation function. I want to think about maybe graphing this accumulation function and thinking about what it has to do with little f. So this is a little bit tricky, but let's take a look at this graph on the left. So this graph on the left is supposed to be a graph of f of x. This is a typo. This should be y equals f of x. Sorry. So we have little f of x, and then on the right hand side, the plan is to graph my accumulation function. By the way, I'm using a capital F here. Could have used capital A. Doesn't really matter. I like to use capital A when I'm thinking about accumulation function, but since the accumulation function is an antiderivative, and it's really common to use capital F as like for an antiderivative, it's fine just to use it for the accumulation function. So I want to graph this, right? I want to graph capital F. It's a function. I could graph it. So how could we do that? Well, whenever we're graphing, one thing you can think about is just trying some points, right? Like if I do like f of 0, I'm going to get some number, and then I can graph that height at x equals 0. So what is f of 0? Well, it's integrating from 0 to 0, which I know that's 0. I don't have to do anything. So when x is 0, like this is x, right? y will be 0. So I'm definitely going to have a point like right here. Let's just try a few other points. Let's try a big F of 1. That's integrating from 0 to 1, my other function. Well, what does that mean? I have to go over to this graph. That's little f. I have to integrate it from 0 to 1. So that means look here, the area there from 0 to 1. I can actually find what that area is just from geometry. Right, this is like a unit square, side length 1. So the area of the whole square is 1, and this triangle is half that area. So that area is 1/2. You could also do like 1/2 base times height. So this is 1/2. So I know that when the input is 1, the output is going to be 1/2. So I'm going to get this point right here. Okay, let's just try a few more points. Maybe let's try f of 1.5. I picked that because that looks like to be about where little f is crossing. So we're integrating from 0 to 1.5 of my little f. And I want to find this area. So I already had 1.5. The black area was 1.5. Now I'm adding on a bit more. We can find the area of that triangle. It should be like 1/2 base times height. Right. 1/2 base times height. The base of it is, it's going, like this is 2 here, right? So the width of the base is 1/2. And the height is 1. So that area is 1/4 altogether. 1/2 times 1/2. So we get 1/4. So that's on top of what we had already. So the 1/4 is like the new extra part plus the 1/2 we got before. So that's 3/4. So I know this area is going up. By the time we get to 1.5, it's up here at 3/4. Okay, so I promise you don't have to do all these calculations every time, but I just want to give you a feel for, you could kind of do this by hand, right? What happens once we get to 1.5? Right, big picture, as I kind of march to the right from 0, I'm accumulating area, I'm getting more and more area. So my output is just growing, right? And in fact, because, my output is just growing. So, but by the time I get 1.5, if I go further, if I go down to here, accumulate like up to 2, say, I'm actually starting to accumulate negative area. Remember, the area that's under the axis counts as negative. So like if I go up to f of 2, I'm actually going to get back to 1/2. Because by the time I get to 2, this chunk of area is canceling out the area that we just got, that extra 1/4. And what's going to be left is just the area that we started with, like from 0 to 1. So I'm going to get back to 1/2 by the time we get to 2. So even though I'm kind of just building more and more area, because I can get negative area, it is going to kind of go up and down. So it's not a coincidence here that I crossed the axis, the left crossed the axis, right at the same value that there's like a peak in this big F function. So that's generally going to happen. Let's actually kind of write that in symbols, right? Little f of x was 0. That corresponded to this peak over here. Remember that, like, we can think about peaks as places where the derivative is equal to 0, right? That was like a Calc 1 thing. If I think about where's the derivative of this equal to 0, well, what is the derivative of this? According to my fundamental theorem, f prime of x is the derivative of 0 to x. But that's just f of x, right? That's my fundamental theorem. So big F prime being 0 happens exactly when little f is equal to 0, right? So little f being 0 is sort of the same thing as big F prime being 0. right? Since big F prime is little f. Like, this is the key relationship that you should have in mind whenever you're thinking about these graphs. Big F prime is little f. Pretty much any question where there's like a graph like this can be answered by keeping this in mind. Big F prime is little f. So, like, when is big F prime 0, for example, it's the same as when f is 0. For the sake of this graph, big F prime being 0, that's where the peak is. So I know that there's going to be a peak here, because that's a place where f is 0. But there's also going to be one here at 4. I know there's going to be a peak here. And over here at 6, I know there's going to be a peak here. So that can already help you kind of start graphing it. We can actually go a little bit further than this, right? Let's imagine thinking about, like, the derivative of f, right? The derivative of f, well, I know that big F prime is little f. So the derivative of little f is the same as big F prime's derivative, right? Right? This is little f prime. Little f is big F prime. So I can replace this little f with big F prime, and its derivative is big F prime's derivative. It's kind of a mouthful, but this is f prime prime, the second derivative, right? So if I'm interested in like if I'm interested in what does the derivative of my graph on the right look like, I just have to look at f. If I'm interested in what's the second derivative of my graph look like, I just have to look at f prime. That's helpful for graphing because we know things about, like, a function is called concave up, right? When its second derivative is positive, that means it looks like this. It's concave down if its second derivative is negative, it looks like that. I know a function is increasing if its derivative is positive, right? Like, so we can relate the graph of big F to the graph of little f. So for example, little f is increasing, or my graph on the left here is positive, for example, all up here until 1.5, which means that big F is increasing all the way up in there into 1.5. Okay, I know big F is increasing. Is it concave up or down? That'll help me draw it. Well, f double prime is f prime. So up until 1 here, f prime is positive. The slope of f is positive, which means that big F will be increasing up until, or concave up until that point. So it'll look, up until 1, it'll be concave up. So it'll look maybe something like that, more of a smile than a frown. But as soon as we hit 1, going from 1 to 1.5, it suddenly, the slope of little f is negative. So f prime, little f prime is less than 0 on that range. So big F double prime is also less than 0 on that range, because they're the same thing. So my big F will be concave down along that range. So it actually kind of goes frowny face now. So concave up and then concave down. So that's kind of enough information to start drawing what big F looks like. It's pretty hard to just reconstruct this graph completely. You can do it, it just kind of takes a while. But we can answer various questions using this relationship. So you might see questions like, when is big F increasing? When is it decreasing? And you can connect it to little f is the point. Yeah. So, so let's maybe just kind of summarize this a little bit. There's kind of a lot going on here. So the key thing is that big F prime is the left. Once you have that, you can kind of write all these things down. Right? F is positive is the same thing as big F prime is positive, because they're the same. But big F prime being positive is the same as big F increasing, because that's like what it means for a function to be increasing. Similarly, if f is increasing, little f is increasing, then its derivative is positive, that's what it means. But because big F prime is little f, that also means that big F double prime is positive, which means big F is concave up. So, just for example, if my little f was like, doing this and then doing this and then doing this, I could start like thinking about big F by saying, okay, first of all, f is for on this first chunk, or on this chunk, little f is positive, so big F will be increasing. Little f's slope is positive, so big F will be concave up. So on this chunk, I know I'm going to be increasing and concave up, which is enough information to sketch something. So if it's increasing and concave up, it's going to look, something like this. And it doesn't have to be a perfect sketch, but it's just kind of giving you an idea. On the next chunk, like here to here, all the same thing is happening, so it'll kind of be doing the same thing. But then once it starts going down, different things will happen. So on the online homework, there's questions about kind of identifying whether it's increasing or decreasing, concave up and down, and this should be enough information to be able to think about those kinds of problems. Cool. Okay, so sort of recap, what we talked about was, our big thing was fundamental theorem 1. By the way, this numbering is not that big of a deal. I'm calling this one fundamental theorem 1. Some books call it one way, call it the other way. But fundamental theorem 1 involved this accumulation function, which we talked a lot about. The main point was, it's a function whose derivative is in fact little f. So given any function, I can build a new antiderivative of it just by doing integrate it. So starting with any function, if I build this new function, that will be an antiderivative of my original function. That was useful for thinking about sort of accumulation, but also in particular useful for finding the area. I can use that idea to build a way to compute this integral, which is really what I'm interested in. Fundamental theorem part 2 is that integral, right? So how do I do an integral? If I don't want to do Riemann sum, I don't have to, because all I have to do is find an antiderivative of your integrand, the thing you're integrating, and then plug in the two bounds a and b. We did a couple examples. So that's the main upshot. We also talked a little bit about thinking about the graphs of this accumulation function versus the graph of the little function, and a way to think about like increasing and decreasing in that context. So that is the main thing. As we go forward, right, because we have this beautiful, beautiful theorem, all we need to do is learn like lots of ways to do this step, to find antiderivatives. So it turns out that's going to be a little bit tricky depending on exactly what little f is. So we're going to spend a lot of time on various tricks and techniques. So I'm not going to talk about them right now, that's where we're headed, but there's sort of a bunch of different names, use of, integration of parts, bunch of fractions, there's all these kind of methods, and we will learn how to use them and apply them in different situations. Cool. So let me know if you have any questions about that, and I will see you next time.